Greetings, the Astro 30 here yet again, and welcome back to AEL. Now if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers guys. Well, I'm looking at this Elektor PA300 amplifier that was published in the November 1995 UK edition of Elektor magazine again today because, well, one, I want to try a couple of experiments to see if I can improve stability. Because I've put a 10 nanofarad ceramic cap here between pins 5 and 8, which, yeah, for audio seems a bit high. I also want to explore why this thing has a prominent hiss behind it through the speaker. It could be because of this bypass 100 nanofarad capacitor across the 47 microfarad capacitor, which is supposed to make it sound brighter. And that's another thing, it did sound a little bit over bright, like a little bit too much high end, more compared to every other frequency. It could be just me too, or the speaker. But that'll be something else I experiment with. I may double up the output stage just to make sure that my idea of how I'm going to do the output stage is going to work and it's not going to blow everything up. But finally, I want to make a correction to the last video. Over there in the center of the screen, the 100k potentiometer, 22k resistor going to the center of that potentiometer for the DC offset components is back on the board. Why? Because I made a mistake. I wired it wrong for a short explanation. So I'm just going to show you now on the whiteboard how this is supposed to be wired according to the data sheet for the DC offset component to actually adjust the DC offset. So I'll give you an example of what I'm talking about here. We have our NE5534 op amp. I'm going to draw as big as possible. Looks like a slice of pizza. So that's pin 3, that's pin 2. That's pin 6, because that's our output point on a single channel op amp. We also have a positive supply rail, which is pin 7. We also have a negative supply rail, which is pin 4. And we have pins 1, 8, that's about 8, and 5. Now, in order to make the DC component offset adjustment work, it's got to be connected right. Because usually between pins 8 and 5, there's a frequency compensation capacitor, which is fine. That can be left in when putting the DC offset components in. In order to make a 100k potentiometer with a 22k coming off of its wiper going to the positive voltage rail here, it it has to be wired right. So we would do between pins 1, which is actually the balance input point, and pins 8, with that going to the positive at 22k. I had it between pins 1 and 5. Well, that's not going to work like that, because I was wondering why this 100k potentiometer was spending most of its time right down in its extreme end of rotation before it actually reduced the DC offset, because the potentiometer, for all intents and purposes, should be sitting around about the halfway mark, maybe a little to the left of it or a little to the right of it, to balance the input stage. Now you can balance it this way, which is one way of doing it. There is another way of doing it. All we've got to do is just move our configuration around a bit. And if we go between pins 1 and 5, instead of pins 1 and 8, and then we take our center wiper with our resistor and we go down to the negative rail, well, the circuit will work exactly the same. So there's two ways of configuring it. You can use it in the negative path or you can use it in the positive path. But you've got to connect it right. You've got to connect one end of the resistor to pin 1 definitely, but the other end has to either connect to pin 8 for a positive adjustment or pin 5 for a negative voltage reference adjustment. And obviously this resistor has to be connected to the right polarity, or it's not going to work. It's just going to give the exact results that we got the other day when I couldn't get it to work. So that was my bad. I got the connections miswired. So I've actually now got it configured as I showed in the first example, so I'll get rid of, you know, those wires for clarity. I've connected it up between pins 1 and 8 for the variable resistor, and the 22K going off to the positive supply rail of the op amp, which is 15 volts. And yeah, we actually now get a proper working circuit. So I will now demonstrate that it is working on camera for you, and then we'll move on to the next thing that I'm planning on doing with this amplifier. And that's how it's supposed to be wired. So I made a mistake. I put it between pins 1 and 5, I believe. And I'm surprised no one in the last video actually tweaked to that and said, no, hang on, that's wrong. Yeah, well, I discovered that after I edited the video and uploaded it, and I was looking at the tab that was still open on my Google page showing the configuration for putting the offset components in, and I realised I had the wrong pin numbers. So what I'm going to do is I'm going to hook this back up to the power supply multimeter. I'm going to purposely set the offset component wrong, and we'll see how well we can actually adjust it down to 0 volt DC. Alright, so first I'll leave the speed low on this one for this. I want it on millivolts. I also want to take that off of auto, and I'll set it to about 500 millivolts. That should be fine. Turn the power supplies on and look for any unusual current draw. No, well, I haven't broken the circuit, so that's alright. So, as we can see, we've got about 6 millivolts of DC offset there. So if I now rotate the 100K potentiometer, I'm going to try the anti-clockwise position first. So it's actually going up. Okay, I'll go clockwise now. As we can see, it's coming down well below 5 millivolts. And if I hold my tongue right, we can get this right down to 0. It's just very, very gentle adjustment towards the end here, and boom, right on the money, 0 volt DC offset on the output. Excellent. That's how it's supposed to work. Now, why am I going to include this trim pot? Well, not that you can really see it, but the NE5534 is just buried under there. Many different batches of this particular IC may vary in electrical characteristics as well as DC offset from batch to batch and from manufacturer to manufacturer. So it would probably be a good idea to include that potentiometer in order for us to properly adjust the DC offset. Just checking that these resistors are beefy enough for the job that it's doing. Apparently so, they're barely warm. Okay, so that's good. The DC offset works now, as it should. I don't know how I managed to mess it up, but I did. Alright, so someone made a comment on the last video about incorrect bypassing, especially with all these wires going everywhere, especially along the output stage here, which is probably what's causing it to ring on the output. I tend to agree. Now, I do have 100 nanofarad capacitors somewhere, there and there, which are bypassing the main supply rails coming into the circuit between positive and negative and ground. But there's no bulk filtering here either. I did try it yesterday and I don't know whether or not I was getting an improvement. But the thing is, the original circuit didn't either. So what I'm going to do I'm going to leave that Zobel network capacitor as 100 nanofarad. I'm going to take this capacitor back out. I'm going to put the 33 back in. I'm going to look at what the output's doing, which may mess with the DC offset, but that's fine for now. And then I'll try a few little experiments with capacitors around the circuit here to see if I can get that ringing to go down. But let me get this configured to the way it was in its, I'm going to say, broken state, and we'll go from there. Well, the 33 picofarad is back in circuit in place of the 10 nanofarad across pins 8 and 5. And I've got the scope probe at the output and ground. I believe it's in times 1. Well, it is now. But annoyingly, there is absolutely nothing going on the scope. There's a slight bit of noise there, but that's it. Doesn't appear to be any oscillation. And DC offset, apart from like 1/10 of a millivolt there, is 0. Now that was up to 20 millivolts yesterday with it ringing, but apparently it's not ringing now. Probably because no one's home and they can't answer the phone, so they gave up. That's a bad joke. So I don't know what's changed. It could be because I've added the DC offset components. Maybe that's having an effect on the circuit somehow. Or the power supply rails being higher than the plus minus 18 volts it was on yesterday is an improvement. I really don't know. That one's got me kind of buggered. So, I probably should connect up the oscillator to it and see if it is actually giving us a clean output, just to, verify. Oscillator is connected. Let's turn these supplies back on. No unusual current draw, nothing on the scope, and DC offset is reasonably okay. So I'll just increase the gain of the oscillator after running it. Yeah, well, look at that. No ringing. And I haven't really done anything to it except add the DC offset components. So I guess that can stay a 33 picofarad as it was in the original design. Next question is it still stable with the 33 that was there instead of the 100? So I'll carefully pull out the 100. Stability is still okay. I'll plug in the 33, if I can get it in there, past that wire. Yep, still stable. That's perplexing. I don't know what's changed, whether I moved something, or whether it was because I moved my ground point for the inputs. Because I've actually now got a wire sticking out the board for the grounds. I was actually connecting across the ground point of that resistor there. But it's only like a pin over from that resistor, so that shouldn't make a difference, I wouldn't have thought. So, very, very odd. However, I might change that to a multi-layer ceramic capacitor. The same as this one over here, same type, same voltage. I mean, 100 would probably be alright, but they're relatively cheap from DigiKey, so I'll get a 33 version of the value of this, which is 470. I'll also get the 47 picofarad capacitor, which is here, going across or bypassing that feedback resistor, as well as a multi-layer ceramic capacitor. The original used polystyrene capacitors instead of disc ceramic, and those multi-layer ceramic capacitors are close to the same sort of characteristics as the polystyrene, so why not use them? So okay, well, I really hate when things mystify me like this, but what I'm going to do is I'm going to ignore all the things coming from eBay telling me stuff is on the way, and being delivered today apparently, which is good. I need some stuff. I'm going to still put in bulk filtering in the supply rails here, because there really should be bulk filtering there. And then I'll move on to the next experiment. Right, the filter capacitors, 100 microfarad each, are in circuit. one going from the positive rail to ground, the other one going from the negative rail to ground. But I noticed something about this 100 nanofarad capacitor here. There it is there. It's starting to bulge. That's like a bubble. It's expanded a bit. Don't know what that's all about. I've never seen these capacitors. They're 100 volt rated. Right, as we can see there, the 100 at the end means 100 volt. I've never seen them do that. Interesting. Alright, so I'm going to turn the circuit on and see if anything else goes up with a bang. I've got one power supply rail powered up for some reason. I've got both power supply rails powered up for some reason. I forgot to turn it off, but our output is still stable, so I didn't damage anything in the process. I wonder why I got a slight spark when I inserted that capacitor. Right, okay, that's what should be there. There should be bulk filtering in the supply rails anyway. That is unusual though. And that was on the positive supply side. And there's only 30 volts there, so I do not know. It looks like it's been stressed somehow. Because I was sticking around on the circuit board there and I noticed it was looking a little bit expanded. Well, that's a dead capacitor now. Next I want to see why this circuit was so hissy yesterday. Also, that linear power supply's transformer is obnoxiously loud. Sonar transformers, can't trust them. So I've got the speaker connected and I've got the positive end disconnected so I can connect it after I've turned the power on. So I'll turn the power on. Okay, 20 mA of current draw. There's a bit of a buzz on the output now. But it's not as hissy as it was yesterday. I reckon it was that 10 nanofarad ceramic capacitor causing it to hiss. So it may have actually changed the frequency response of the amplifier too. I mean, apart from a buzz, which is probably coming from the input, there's nothing happening. Okay. I mean, there is a slight, well, there's no turn-off transient either. There is a slight hiss there in the background, but it's not as obnoxious as it was yesterday. Okay, let me hook this up to some audio and see if it sounds any different than it did yesterday, because the highs were pretty shrill. But again, that may have been attributed to that 10 nanofarad capacitor, so fingers crossed. Okay, got the audio input connected. Repower it and reconnect the speaker. There's still a buzz behind it, but it could be all the exposed wiring and the power supply as well. So let's play a track if I so can. Sounds alright. Let's play another one. Maybe, maybe not. Let's try again. Well, it doesn't sound as trebly as it did yesterday. Okay, so let's do a comparison test. I'm going to remove the 100 nanofarad bypass capacitor out of circuit and see if that changes the sound quality. Not really. No difference. Alright then. Well, that's just not proving anything. But yeah, it's not as shrill as it was yesterday. I reckon it's because of that 10 nanofarad capacitor being changed back to 33 picofarad as the reason why. Now, why it's no longer ringing on the output when I changed both capacitors back to their original values, 33 picofarad versus 33 nanofarad in the sidewall, you tell me. I mean, I'm not going to complain. But if you could also tell me how that happened, I would be really glad of that, because I have never seen a 100 nanofarad capacitor, 100 volt MKT capacitor do that before. Never. It's like it was starting to bulge and leak, is what it looks like it's doing. But that would have to be because it was either severely overvolted, or there's an issue with the chemical reactions going on inside of that capacitor when current's flowing. I don't know. It's the only capacitor that did it. Maybe it happened during my power testing when the current was up to 1.5 amps into 4 ohms, but it shouldn't have done that. No other amplifier that uses these capacitors, and they're from the same supplier, have done that. It's the first time I've ever seen that. So if you can explain what's going on there, that'd be great. So next I should probably try paralleling up the output stage, but that's going to be a little bit more difficult because I don't know how I'm going to do it. Because, I mean, I've got room to put the extra degeneration resistors in for the positive and minus rails, but I've got no extra space on this heatsink for the transistors. Well, I've got one hole there, so I can put one transistor on there, but I need two. I'll have to think about this for a few minutes off camera of how I'm going to achieve this, if I do it at all. I'm pretty sure it is going to work. It is the same as a complementary feedback pair with the collectors being joined all together and the bases being all joined together through a set of degeneration resistors before the output, and having two extra degeneration resistors in the emitters. It's the same thing. All we're doing is we're reversing it around, so it's now the bases and the emitters connected together, and the collectors being degenerated or having a current limiting resistor on it. I don't see any difference of it. I mean, the emitters are now going to be sharing these output degeneration resistors, but it shouldn't really affect it that much. Yeah. So let me think about this off camera for a few minutes and I'll see what I can come up with. Well, I've got an old heatsink out of a Technics amplifier which had a chip on it with the extra two sets of output transistors mounted to, so that's actually a more better heatsink than what it's sitting on. I've just got the end of the heatsink propped up so it's not tilting backwards and putting stress on the wires. And they're paralleled up with the first set with their own collector resistors. And the emitters go back to these degeneration resistors up here. So I'll draw a diagram at the end just so you can see what I'm talking about. I don't want to make this video too much longer, so I just want to prove that this concept is going to work and work fine. So I'm going to do a preliminary power up test, and I've limited the supplies to around about 100 mA or so, so I'll turn them on. Still drawing about 19 mA. So we look for the magic smoke or any unusual heating. Nothing appears to be happening. Okay, so let me hook up the multimeter back across the output. We'll look at the DC offset without pulling shit off the bench. So I'll connect it to, not like that, connect it there, and I've lost my negative lead. Where's that gone? Right there. Connect that to ground. According to that, that hasn't changed. That's still 0 volt. Alright, excellent. So next I should probably load it and maybe do a power test on it. So I'm going to turn my supplies off before I do anything, and I'm going to need to increase that current limit back up to where it was, which was 2 amps, and wind these right back up. It only draws around about 1.2 amps, well it did originally with the 2 transistors, into 8 ohms. So let me rehook up the oscillator and dummy load. I'm not going to worry too much about doing a 4 ohm test, but I just wanted to make sure that, you know, nothing's going to start smoking. Like one set of transistors is going to like get hotter than the other, that sort of thing. So I'll get that all set up and we'll have a look at what's happening. Okay, 8 ohm load is connected now. Stand by for blowing up and laughing. No unusual current draw, still sitting around about 19 mA. Excellent. Nothing really weird going on the oscilloscope. So I'll run the oscillator. Yep, we've got an output. Okay, so it's starting to look like a project that Frankenstein or something. So I'm going to ramp this up till it clips. You can watch this in case anything pops. Till it clips, which is there. Excellent. Won't do that for too long, but it's about 17.4 volt RMS. It's about the same as it was the last time, 37.8 watts now. You know, it's only gained about probably a watt and a bit. But that's not the point to paralleling up the output stage. The only reason we're paralleling the output stage is so it can share the current evenly and have a better time driving a lower impedance load such as 4 ohms, so that you can get the maximum amount of power out of the amplifier as possible. So I'm happy. There's not much else I can really do to this thing. I've put it through the ringer, like literally put it through the ringer, and I can't think of anything else to modify it. Now it's gone back to the changes that it was to start with. I've removed the 33 picofarad and the 33 nanofarad, so it's now as the circuit diagram is, just with the addition of the 2 bulk filtering capacitors plus rearranging the output stage. So I'm going to now finish this video off by drawing up the output stage on the whiteboard so you can see what's been changed and why I did it. Alright, as crooked as that is, it's just because there's stuff in the way at the moment. I can't get the tripod straight on the desk. So, I'll draw the output stage. So, we've got, what have we got? Well, this is just basic output stage. I'm not going to draw the thing as it is in the diagram because there's no point. But we've got a NPN driver transistor here. That goes off to the biasing network and everything. This is our plus volt rail. These 2 drivers do actually go through a resistor in the emitters. And here is our PMP driver. And that goes off to our negative voltage rail. And as it's a Darlington configuration, we've got our first output transistor, which is also NPN. Coming off, we've got RCD, which stands for resistor collector degeneration. We then go through RED, which is resistor emitter degeneration. all these resistors I'm showing here are 0.22 ohms. This one's not, so we ignore that for now. We go through another degeneration resistor, which is RED. And this is our output point. And then we go into our PNP output transistor. That's also RCD. Now, so far that looks like how I had it to start with. We just got extra resistors here in the degeneration circuit. And now when we parallel, what I have done is connected another transistor, base to base. That's NPN. Got another RCD. And I have connected them emitter to emitter. So the same's true over here. We've got our base takeoff point here. That goes down into our PNP output transistor, RCD, and I'll redraw that a little bit clearer. My pen's deciding not to work. And then we connect the emitters together, as well as the bases. I mean, I hope that's clear enough. So this is NPN, NPN, PNP, PNP. So that's how it's configured. So the emitters are going through these two same emitter degeneration resistors, but each collector has its own degeneration resistor, so that these two transistors and these two transistors will share the current evenly. If I was to just connect this collector to that collector, well, all the current's going to be flowing through this one resistor. Or if these two resistors weren't even here and they just went straight to the positive voltage rail, for instance, well, these transistors are not going to share the current evenly. I did find by connecting the emitters together through the same degeneration resistors, IQ, which is the current flowing through this circuit, doesn't change. That's its quiescent current, by the way. So the quiescent current didn't change by paralleling these transistors up like this with the same degeneration resistors in the emitters instead of separate ones. Now, why have I used the same emitter degeneration resistors and separate collector resistors? Well, it's simple. These 2 points go back off to the VI limiter, and the VI limiter is measuring the current or monitoring the current flowing through these 2 resistors, as well as the output bus. And once the current flowing through these resistors is greater than what's on the output bus, we're in a short circuit condition. Problem with that is it's only monitoring one set of emitter degeneration resistors, because the original circuit had on the second transistor its own emitter degeneration resistors, but it's not measuring the current on those degeneration resistors. So in the likelihood the current's going to find the quickest way it can, or the shortest path, it's most likely going to go through this outer transistor pair first, and its degeneration resistors, and the current limiter is not going to even really notice any difference until these start conducting and pushing current through these resistors. So it can monitor both at the same time. Well, we just use single resistors here and just add extra resistors here in the collectors for degeneration and current sharing. And it's the same as if this was connected to the rail, that was connected to the rail, and the resistors were here to the output bus. It's no physical difference, it's just in a different place in the circuit, that's it. But it still does the same job. So anyway, that's explaining why I've changed it and how I've changed it. And so I'm not going to do much more on this, probably make up a PCB. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.